Hello everyone and welcome to this lecture. Today we are going to talk about a totally new thing, and this is something called as the eigenvalue problem. So this eigen word is actually a German word and it means proper. So eigen means proper or characteristic. So the reason for this giving this problem that we'll talk about in a few minutes, giving this name has its own reasons, and when we see that in terms of mathematical operations it will be more clear to you guys. So let's get started. So what is this eigenvalue problem, right? So let's say you have a linear operator. I have a linear operator that is defined as, let's say, omega. Okay, it doesn't look very good, so let's call our linear operator omega, and there might be set of vectors that forms a vector space. So what an operator does, from our past lectures we know that if you have a vector, let's say v, or in this case let's call them small omegas, and a linear operator can act on them, right? And if this is a non-trivial operator, non-trivial, this means omega is not the identity operator or the zero operator. So this is a non-trivial operator. So if this is true, that omega is not a non-trivial operator, then this ket over here, this ket undergoes non-trivial change. Right? And let's say after the operator acted on omega, it is transferring it to omega prime. This is what linear operation does, and the very familiar example is the matrix multiplication, where omega can be, let's say omega can be a n cross n matrix, and this small omega over here can be a n cross 1 matrix, that is a column matrix, right? Or omega even can be a differential operator. And this can be a function. So this differential operator and this function thing will come naturally when we take the vector space to have infinite dimensions. That is, it's a infinite dimensional vector space. But for now, let's focus on the finite dimensional case. So this is what happens usually, but there exists, under some really well defined conditions, there might exist states. So states means this gets states that gets rescaled under, oops, I shouldn't have written there because, so let me just, okay, so there exists some states that is gets like this, which gets rescaled when they are acted with some linear operator omega. So mathematically, this means if you have a omega, that is the operator, so let me emphasize it, this is my operator, this is my state, and the term rescaling means, let's say you have omega over here, this is a scalar number, and finally you have something like this. So this equation is something called the eigenvalue equation. Let me just highlight it with another color. Oops. This equation is called the eigenvalue equation, or the proper value equation, or the characteristic not the characteristic equation, but that is something that will come later. So this equation is something that we are calling the eigenvalue equation, and this scalar over here, it will be our eigenvalue, and this ket over here, that is this one and this one, let me just mark it with red color, this one and this one, these are called eigenkets or eigenstates if you talk in terms of physics, because in physics that's what we use, that is, we use kets to represent a state, or so to say, we use vectors and vector spaces to represent some states. So let me again explain the whole thing in a clean manner, and the reason for this equation's significance will be evident a bit later when I show you the geometrical interpretation of it. So our eigenvalue equation will be, oh yes, there is one more thing, a slight minor thing, that is, you can see that there is a matrix over here and a column vector over here, right? And here you have another column vector times a scalar, but implicitly there can be a identity matrix over here as well. So let me just write it again, and that will be proven useful when we try to find out the characteristic equation, that is, when we will try to determine the eigenvalues and the eigenvectors of a linear operator. So let me just write it down it again. Our eigenvalue equation is omega, this is our operator again, this is our state, and let's say this has eigenvalue small omega and the eigenket as small omega with the ket, and again this is, so notice that this ket is the eigenket for the operator omega, because if you take another ket, let's say A, and it doesn't get rescaled after you apply this operator omega onto it, it might get transformed as this A prime. So this is not an eigenvalue equation. So let me just write it again. This is not an eigenvalue equation. Oops. This is not an eigenvalue equation. This is our eigenvalue equation over here. Because see, think of it like this. So now I'll discuss the geometrical picture of it. So let's give it a title, geometrical picture. So let's say omega will represent some rotation operator, or you know what, let's not take rotation operator as an example because you might get confused. So omega is some operator, let's say, and I will have a I will represent the eigenket as blue color over here, and I will represent with small omega. So this will be my eigenket, and with green color I will represent another state. So this is some other state, and what And let's consider a 3D Euclidean space like this, just to show you a picture. So let's say this is my x, this is my y, this is my z axes, and the two vectors I have labeled here, they are represented by, let's say this is omega and let's say this is my a. And now what I will do, I will take this operator from here and I will act on both the omega and the a. This is what I want to do, and let's say I did that. What will happen now is that omega will get shifted. So let me use a bit bold color to indicate the shifted omega. So this will be a bit rescaled. So up to this part it was just 1 dot or 1 times omega, and let's say this time it became 3. It's 3 omega. So the 3 omega will be this dashed line from the origin. It doesn't mean it's getting parallel or something, so it means it's getting rescaled. Or if you have a -3, this means it's shrinking 3 times, and so on. But when you apply omega to this a might get rotated. So let me use the another color. So let's say this is my rotation angle theta, and then this is my a prime. So this is the difference between the eigenvectors and the non-eigenvectors for a specific operator. And yes, the eigenvalues and the eigenvectors, both of them will come from the operator itself. And finally, I want, since this is the geometrical picture I have just only discussed, let me give you a physical motivation, or so to say physical consequence of the eigenvalue equation. So the first thing that I want to talk about is very simple, and it's also geometrical as well. So let's say I have a cube like this, and each of the arm of this cube is given by some vector, right? Since this is a cube, all of them will be same. So I actually need 3 vectors to construct this cube, or so to say just only one, because if you think in terms of x, y and z axis, let's say this is x, y, z, and this cube is over here, right? And this cube is just, let's say it's denoted by this cube vector thing. It might be anything. In reality this will be a column vector, that is the each one of these arms will be one column vector, but let's not focus on that. Let's just take this big cube over here to be written as the state cube. And what I want to do now is that I want to use some operator, let's say capital A, and if this cube, okay, not here, if cube is an eigenvector, that is each of the arms of the cube is an eigenvector of this A, then let's say A of cube will give me 3 times cube. Obviously there is an identity matrix over here, but you can suppress that, we'll use it later. So what does this mean, right? It means that each of these arms over here, let me just use some red dots, yeah, each of these arms over here will get rescaled. So after you do this operation, that is over here, let me use it. After doing this, since each of this arm is getting longer than before, that is 3 times longer, what you expect is that the volume of the cube is now 3 times bigger than the volume of the cube that used to be before. So geometrically, this means this cube is there, but now it's a bit bigger, though it doesn't look that big. Sorry for that. So if this cube's volume is V, this cube's volume will be 3V. So notice something interesting, that the shape of the cube is not changing. So let's note that down. That means the shape of the cube is not changing. This is something we are noticing. But what if we had another operator called P, which acts on each arm of the cube, and it gives something, let's say Q prime, where Q prime is a rotated version of arm A. This means each of these arms will now be rotated. So let me draw another picture and show it to you what will happen if this is the case. So this is my cube again. This was the initial state of the cube. That means it was a cube all along, right? Okay, let me just bold it out so that you can distinguish. And let's say this is an A, this is another A, and another, and so on. So after acting with B operator over here, this A, let's say it will get rotated to this way, and this one will get rotated in that way, this one will be rotated in that way, and so on. So what will happen is that the cube won't be a cube anymore. It will become a parallelepiped. Okay, so the drawing is pretty horrible, but you get the idea. Yeah, the drawing is very horrible. So here the shape of the cube is altered. So far we have noticed these two things, right? And now let's try to make a decision out of it. So eigenvalues or eigenvector, that is, if you have an operator and you have some eigenvectors, then eigenvectors correspond to, okay, let me just write for a specific operator. For a specific operator, eigenvectors corresponds to states that does not get disturbed while trying to measure something about that state. So what does this statement mean? This means, let's say you, let's say there is something inside this cube, that is from this cube you want to get some physical information, and you don't want to disturb the cube. By disturbing, I mean doing any kind of experiment that might destroy the cube, that might change its shape, and so on. So that's why you have to take some measurement, that is some operator as A, that won't disturb its state. So that's the reason we are calling these eigenvectors as states for a specific operator. And now come to think of it, when you think in terms of physics, let's say you have a Okay, how do I draw an electron? Okay, so this is an electron, let's say. This is an electron, and what you want to do now is that you want to hit it with light. Why? Because you want to measure the position of the electron. So applying this light or hitting the electron with light is equivalent of applying an operator. So hitting the electron, hitting the E minus with light or gamma. Okay, that doesn't look like gamma. With gamma is equivalent of choosing an operator that will correspond to some measurement. Obviously not all operator will correspond to measurement, and not all operator will give us something observable. We will classify that later, but for now let's just think of these things really simply. And this electron over here, this is representing, so this is representing an operator, let's say A, and this is representing some state E. I just denote it by E, this electron itself. So if you can measure this electron's position, so I want to know the position, right? So what you do, you just hit it with light, and the electron, let's say, absorbs the light, and it also it goes to the excited level and it drops down, and you assuming that this absorption and radiation time is very negligible, you just calculate the time difference between it, right? And the more you hit it with light, the better you expect the position to be. That is the resolution that you are measuring, the resolution for the device that you are measuring with, that will increase. So the idea is that you are hitting it with more light, and you are taking, let's say, 200 or 300 measures and so on, and then you can finally get some stable value that is indicating the position of the electron, right? And that's why I'm saying that if it gets rescaled, only then you can measure the position over here. So this is what an eigenvalue problem looks like in physics. So let's say instead of measuring the position, let's say I want to measure the energy now. So let's try to measure the energy. Let's try to measure the energy of this E minus. So this Hamiltonian operator, okay, let's not use the hat. This Hamiltonian operator will give you the energy eigenstates. Hamiltonian is analogous to let's say total energy in classical physics, and here as well. In fact, in quantum physics it's known as the time translation generator and so on, but for simplicity it's just an operator, and it just gives me some energy eigenvalues. And the energy eigenvalues, let's say, since I call this E to be my position eigenstates, I want to call the n, let's say this, that is, if you take quantum mechanics, these are sometimes called the number or the number of quantas. So let's just keep that aside, and let's just call it my eigenvector for the Hamiltonian operator. So if you want to know the energy, so if you want to know the energy of the n state, that is this n which is corresponding to this electron over here, all you need to do, you have to apply this Hamiltonian over n, and it will spit out some energy. Let's say I'm denoting this with E underscore n, and this is everything. And in fact, there is also something called an expectation value that is coming from this equation over here, and it is denoted by this sandwiching. And you can normalize them, normalize this. We'll see in later how we can do this. Obviously, if you remember how to normalize a vector, that is just take the vector itself and divide by its norm. And analogously, you can normalize these n vectors or n kets over here using the bracket notation as well. So let's just cut it down. So the expectation value for the Hamiltonian is just energy. So it means there is some let's say some physical object, let's say a truck. Instead of an electron, let's think of a truck. So a truck is let's say moving in time, or it's staying still, and you are trying to do some experiment that will reveal the position of the truck or the speed of the truck or the total energy of the truck. So since this is an Hamiltonian operator, this will give you an energy, the energy of the object that you are interested in. If it was a position operator, let's say position operator denoted by x, and let's call its eigenkets as small x. This would give you the small x, this means the position. The notations might seem a bit confusing, but when we deal with the numerical things, it will become clear that what are these things. The position is just the expectation value of this position operator, that is denoted by capital X, or you can also give some hats over here if you like. So that's why these eigenstates and eigenvalues of an operator are really important, because once you now let's take another example, and this will probably be the final example for today. Let's think of a polarizer, and it can polarize light in the z and the x axis. Is it x? Yeah, let's call it x. And let's say you have light coming like this in all frequencies, in all the ways, randomly oriented. I don't know. Okay, it seems very bad. It seems very bad. So let's say light is coming like this. And you can draw more if you want. And these are my lights, and this is my polarizer. And this is something equivalent to an operator, which is equivalent to a measuring device. Let's say for this experiment, it's just a filtering device, right? And you can see that it will only let the lights which are polarized in the z-axis, that is pz and px, these are polarized light. So it will only let the lights like let's say this blue one is my this is polarized in x-axis. So let me just draw this whole thing together. Okay, so this is polarized in x-axis px, and this yellow one is polarized in z-axis. And when this random light with the random polarization orientation will hit this polarizer, what will happen is that only the yellow one will pass, and the blue one will pass as well. But the rest, that is the red line, the black lines, all of them will get blocked out. Even let's draw a color with a rainbow. I mean, yeah, all of these will get blocked out by this polarizer. So yeah, so these portions are blocked, only these are open. So that's why we can say this x and z, these two axes can be thought of as the eigenkets for this polarizer, or so to say, these light rays, that is the blue one and the yellow one, the states they are in, that's an eigenstate that will correspond to this polarizer. or that is a polarization operation, or whatever you want to call it. That is for this experiment. Those are my proper states. That is, I can actually let them pass. And the others, so that's why the idea that eigenstates will depend on what is the operator that you are dealing with. So I think this will be it for today, and we'll talk more, and everything will be more clear when we deal with these things numerically, and we'll see some applications of it in quantum mechanics. So this is it for today, and thank you.